Hey guys. Oh, hey, it's 8 p.m. Is this working? Am I on? Am I live? Are we live?
You know what I realized I looked like yesterday?
Hmm.
Once upon a time.
Once upon a time. Yeah, that's you. And we're live. I think. Alright. Well, today I'm gonna be studying for my exam. It's gonna be at 8 o'clock in the morning. I should have started studying earlier, but hey, life happens. Studying doesn't happen. But now it is. That's the important part. Bright side, everyone. This is the first exam for, let's see, ME 380 for what? What is this? Manufacturing? Hopefully I can, uh-oh. No, don't look at that. Oh, I'll cut that later. Start at the top. So yeah, we're actually going to be following, the textbook, a textbook. It is, I don't know what it is. Some textbook from somewhere. You probably saw it earlier, but whatever. Fundamentals of Modern Manufacturing by Mikhail P. Groover. 6th edition, I think. Alright, let's look at manufacturing. Oh yeah, this is a book. Have it on Kindle. Alright, what's manufacturing? Manufacturing, there's two basic types of manufacturing, right? There's, oh, and the professor gave us a study guide thing. That's not it. Where is it? Here. Major topics. Main topics. In review. Yeah, you can have one. Yeah, they're pretty cool. Can I call you Crisco? Because you're shortening. Yep. What? This this is only halfway for education. This is more for entertainment, for my entertainment. Maybe I should turn this app back to entertainment instead of education. Um I have no credentials. I am just a student in mechanical engineering. So I'm not teaching anything because I'm not a teacher. No! There's economics, the economic way of viewing manufacturing, where you put stuff value into a thing, so that thing you can sell it for more than what it costs you to get it for.
How many can I have?
Yeah, as many as you want, Chris.
Is there always chicken on it?
Chicken?
Is it chicken?
I don't know.
Why are there chicken on it?
There's a lot of stuff on it. There was ham on it, and I was like, "What? There's ham on it?"
It's always in the box.
Yeah, Papa. Was it? I don't know. Yes, I saw it in the. Wait, no, I don't know. I saw it in the box this morning. I think yeah, Papa John's gives peppers, right? Not sponsored. Sponsor me, Papa. Oh wait, no. I don't know if I want to be sponsored by Papa anymore. They called him racist. And we don't deal with people who are called racist, like PewDiePie. No! No, you stop it right now. No, let's not get political. Okay, technological. Manufacturing industries. You got primary, secondary, and tertiary. So for primary industries, think about the people that go outside and get the stuff. You got the agriculture, they grow the foods. Or the forestry, they cut down the trees. Fishing. They stick their hands in the rivers for the fish. This is. You don't need to know much about that. Don't know about that. The manufactured products. Don't know about that. I mean, don't need to know about that. Okay. So,
Production utensils.
a company can choose between product variety or production quantity. Or if you're Jeff Bezos, you can do both at the same time. Huh? You can look at Apple, for example. Their product variety is rather low. Product variety low. Oh, sorry. What? Product variety low, down over here. So you follow the line and you're like, oh hey, the quantity's high. They sell a lot of the same. They only have like what? They only really focus on what, 2 iPhones at a time? And they sell so many of them, and it's crazy how many they sell. That's an example. Or a high variety of products, like what's a company that has a large variety of products? Toys. Samsung? They're really big though. They sell a lot of phones.
And washing machine.
They also sell a lot of different types of phones. Yeah, they sell washing machines. The washing machines are flashy, but okay. I cannot attest to their longevity. But this isn't a washing machine review channel. This is a Watch Perry struggle channel.
Do that.
Huh?
Washing machine is good.
Washes them good, real good. Materials, processes, blah blah blah. Mining, blah blah blah. Historical materials, blah blah blah. Computers are powerful classes of material. Okay, cool. Metals. One of the 3 major manufacturing materials. First, you got the metals, you got the ceramics, and you got the polymers. But let's talk about metals. You may be familiar with metals and what metals are. There's metal. There's cold metal. There's magnetic metal. Oh, here. There's Fe, Al, Q, Ti, Au, and N, otherwise known as iron, aluminium for you Brits and non-North Americans. I call it aluminum. See you later. Copper, titanium, AU. Come back here with my gold, and nickel. We'll talk a lot about metals. Actually, I think this first test is a lot about metals. You got ceramics. Ceramics are really hard. Oh wait, no, yeah. Metals. The atoms are highly ordered. You find them in like crystal structures. They have long range order and stuff. They're very structured. Mostly because of how they bond. I guess this is all because of how the atoms bond. Ceramics. Metal plus non-metal elements. Oh yeah, metal. Metal, non-metal. Get really hard. You know, glass is a ceramic. You're familiar with ceramics. Ceramic is ceramic, pottery, all that stuff. Really strong, really hard, but it cracks. Explodes. Doesn't really, not the technical way of exploding. It cracks and shatters, there we go. Optical properties, whatever. Polymers. I don't know very much about polymers, but yet, because that's in a later chapter. Ductile, inert, thermally stable, whatever. Low thermal stability, oops. Composites. Now you can mix things together and make composites. Advanced materials. These are really cool, awesome materials that are too advanced for me. So there's 2 basic types of manufacturing processes. There's processing operations that transform a thing, like a block of aluminum, melt it down, and push it through a hole to get extruded aluminum. Or bending sheet metal to make a thing. And then there's assembly where you get the sheet metal that's bent, and then you, I don't know, put screws on them or weld them together, join two or more components to create a new entity. Those are two manufacturing processes, two different manufacturing processes. Blah 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 blah. Trends, blah blah blah. Six Sigma, whatever. All right, moving on. Nature of materials. Atomic structure, the atoms and stuff. Atoms are expensive and important. Got interatomic bonding, ordering of atoms and ions and whatever. Where am I at? Oh, jeez. These pages. Yeah, a couple pages in my notebook are torn off pages that I kind of just pushed back in to the binding because I took the notes in the wrong notebook and I wanted to have the pages in the right page. Oh, shoot! I forgot that way I can have a cheat sheet. All right, let's make that around. Cool. Huh? What? All right. Let's find out what we need to add to this cheat sheet. What are we gonna call this? Oh wait, no, there's no room. We'll add some stuff to this later. Let's look at this. Chapter 2, Nature of Materials. Alright, you got the atomic structure, arrangement of atoms, how they affect bonding. Bonding is very important. And atoms and ion order in space. This isn't talking about outer space. This is talking about space in general, like room. Material properties. Okay, material properties are related to electron configuration. You know, the 1s2, the 2s2, the 2s2, 2s2, 2p6, 3s2. Had a something 3d10. I'm not a chemist. I did poorly in chemistry. Pay attention in chemistry, kids. Okay. Atomic model. This picture is technically a lie. Electrons float in clouds with energy levels and stuff. What is my credibility? My credibility is that I took a chemistry class before in freshman year. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. I didn't say I didn't do well. Did I say that? Oh. Well. I didn't do terribly. That's fine. That's beside the point, because all the chemistry I need to know right now is here. It's fine. It's all good. Fine and dandy. Valence electrons. Valence electrons are the electrons that you find at the outer shells, or the outer energy levels that atoms have. Filled shells are more stable, and atoms want to be stable because stable. They like each other. Valence electrons determine basically all the properties of an element, because that's how the elements interact with other ones, with their valence electrons. Got the periodic table, got all this group stuff. Maybe I should just have, no, that's silly. Atomic bonding and primary bonding. You got the ionic bonds. Wait, no, primary bonding. Primary bonding happens between elements. This is going to be important for the different types of materials. So ionic bonding generally happens in ceramics. You got a metal and you get a non-metal, then they like each other a lot. You got the cation and the anion. Cations are the positive. That means they give away the electron. That's gonna be the metal sorry. It's usually the non-metal, I think. Nope, says right here, cation, usually the metal. So the cation is usually the metal. It gives away its electron to the anion. You can remember this by noting that cations are positive because they're cats. But that doesn't work because I like to pronounce them in my head as cation and anion. It sounds cooler and sillier. It also sounds a lot stupider, and it's wrong. Call them cations or anions, not cations or anions. Ionic bonding it's a direct transfer of electrons. So no. There's no mommy and daddy here. There's just a metal and a non-metal. The metal gives its electron to the non-metal. Oh my god, this is marriage. They're stuck together really strong. And because of this, ionic bonding is the strongest of the primary bonding types that we covered. Because of this, you can guess that the materials that have ionic bonds within them are really strong. Probably brittle. Ergo, la 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 la, ceramics. Covalent bonding. Covalent bonding is different. This is what you should strive for. Sharing. They share electrons. They have similar electronegativity. Oh yeah, ionic bonding requires pretty different electronegativities for one atom to just take another atom's electron. Electronegativity is an element's or an atom's tendency to hug electrons tighter. No! This isn't fake news. This is not a news channel. I don't want to do research. Covalent bonding. That's when the atoms are similarly electronegative. I don't yell. I yell at everyone. They share electrons. Okay? It's usually a nonmetal with a nonmetal. Happens to elements that are close to each other on the periodic table. They can be seen in any material class. So you can have metals that go with covalent bonding, I guess. Ceramics that have covalent bonding. But we're going to associate this type of bonding with polymers. Stretchy, bouncy, melts a lot, and stuff like that. Now, metallic bonding. This is the type of bonding that we're going to associate with metals. Who'd have thunk it? You know they did surgery on a grape like 10 years ago? Actually, I can look that up. Grape surgery. See, they turned it into a meme. This was so old. I think Vsauce brought it up first, or that's where I got it from. Picked out all the olives and mushrooms?
There's a lot hiding under the pepperoni.
I like olives and mushrooms.
I like them, but I don't like them right now.
I like them most of the time. The Da Vinci surgical system is a robotic surgical system made by the American company Intuitive Surgical, approved by the Food and Drug Administration, also known as the FDA, in 2000, the year 2000. Blah, 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 blah. It was cleared into the year 2000, almost 20 years ago. When did they do the thing with the grape? Let's find out. Grape. Wait, I'm pretty sure. What? What? Vinci, grape. Whatever. Who's distracting me? Yeah, subscribe to PewDiePie. We have to be T-Series. Metallic bonding. Metallic bonding is actually really strange compared to covalent and ionic. It's when the metal atoms get really close to each other and their electrons just kind of fuse, and it's like it turns for instead of each atom having like an electron cloud, it becomes a whole bunch of atoms that are really close to each other that make an electron C. It's not gross. Come on. Now let's look at secondary. But oh yeah, because of this, the electrons can flow freely. So no. Stop it. Stop it. The electrons can flow freely, meaning that the metals or the stuff that goes through metallic bonding, metals, have good electrical and thermal conductivity. Relatively speaking. Oh, hey, Panda. Secondary bonding. This happens between molecules. You got the London forces. That's where the atoms shift together and they kind of go to one side, and the electrons kind of go to the other side because they do that. The molecules, the parts that have the positive, they repel each other, so they kind of want to stay away, and the minuses attract each other, so they like each other. You get them a lot of polymers, between polymers. Hydrogen bonding happens in water. That's when the hydrogen is small, it attracts the other side. Ordering, you got crystalline and non-crystalline. What is a DCA? Manner in which atoms are located regular with a unit cell. Basic geometry. Oh yeah, we know what unit cells are, right? I didn't say that. That is not true. You know what? Yes, that is true. At the end of the video, I'm gonna be giving away some Papa John's coupon codes. So stay tuned. I didn't lie. Wait, no, I didn't even lie. I said this video isn't sponsored by Papa John's. Okay. Unit cells makes a pattern. Pattern's repeated. Repeated pattern gives a crystal. Whatever. Basically all metals, many ceramics, some polymers. You got the BCC, District Standard Assessment.
Got silenced.
Oh, one of those. Huh?
I got silenced.
Why? Oh, okay. Well,
I was sending too many messages.
it's okay. I unchecked that box. Oh my god. I'm gonna check that box again.
No.
You got the BCC, you got the FCC, you got the HCP. You also got the CGP Grey, another great YouTube channel that you should maybe check out if you like learning about stuff. No, I will not fight you in real life. These are different crystal forms that they can take. There's more than these three, but I guess these three are these three are most common. Let's look at the crystal structures for common metals. I probably don't need to know that. Wait, types of crystal structures? Okay, let's study this. You should. Body-centered cubic. Alright, we can remember that by its name, body-centered cubic. That means you draw a cube and you put all the atoms. Each atom gets a vertex, and one gets in the middle of the body, in the center. Now you got face-centered cubic. It's kind of the same, except you draw a cube, put it on all the vertices, and then you put one in the center of all the faces. You get higher density packing. Yeah, studying's pretty hard. Then you got the hexagonal close packed. How do I study? My professor gives me this and a whole bunch of lecture slides. Hexagonally close pack? That's where you get a hexagon and you pack them real close.
Really?
Yep. These are actually really self-explanatory. Just gotta remember what they stand for.
I wish my math is self-explanatory.
What math is self-explanatory? Point slope form. That form is where you get a point and a slope and it makes a line.
You know how I messed up?
Hmm.
I forgot the formula for slope.
Slope intercept? Oh, you forgot how to find slope?
I think we remember if it was y on top or x on top.
What'd you do?
I think I put y on top.
That's good. Because it's rise over run.
Duh.
Did you forget that? Rise over run! Because you gotta give them an uppercut, and then as their body's coming down, you punch them forward, and then they go whoosh.
I know the formula, but it's just when I was doing my homework, I didn't need the. I was just doing it because I knew it.
Alright, let's look at some common metals. Chromium, iron, molybdenum, and tungsten. Tungsten is really strong. Aluminum, magnesia, whatever. Probably don't need to learn that. Know that. Imperfections in crystals. Ah, yes, defects. Defects are really important because they are. The types of defects that I need to know are... Maybe I should write those down. You got point defects, line defects, and surface or interfacial defects. Fancy. So point defects are... Wait, I can just copy these pictures. Just take a screenshot of this and slap it over here. Uh-oh. Come back! No!
Sad.
Take a picture of this. Point defects. A, vacancy. B, oh, yeah, I guess I should have this too.
Is that 80K?
80K? What does that mean? 80,000? ADK is what?
80K.
80K? What's that?
ATK.
ATK? Attack?
ATIEKY.
ATAKY? ATIEKAY. What? What are you?
Katie.
Oh, no. don't know. Frankel defect. That's a funny name. Oh wait, I have to make sure that I'm allowed to put pictures on my cheat sheet. Why does he call it a cheat sheet? Does he?
Not cheating if it's allowed.
Does he like what? The test will cover topics 1 through 7 of the notes posted on Blackboard. You're allowed to use a cheat sheet during the exam. You may write whatever you want on one side. It must be turned in with my exam. All right. Well, since I can write whatever I want, looks like I'll just write all the answers. Now I just gotta figure out what the questions are. I think I can figure this out. All right, margins. You can just be really big. I think my printer can probably handle it, but that's fine.
Would the quiz like that work?
Huh?
Would the quiz like that work?
Where what?
Given the answers and you have to find the question?
That's just multiple choice. Wait, that would suck. I mean, especially if it's math, it would suck. Wait, no, it wouldn't even make a difference. It's just an answer bank. You would still have to solve them all anyway. Imperfections in crystal structure involving either a single atom or a small number of atoms. Okay. Either one of them goes away or you add some. Vacancy, ion pair, vacancy, ion pair. Oh, yeah. Because the big one and the small one pop out and they probably became an ion outside. Interstitial C. Interstitial C. That's hard to say. Good thing there's no vocal part of the exam. Frankel defect, that's when this is moved over here. Cool. Line defects, also known as dislocations, can take two forms. You got the edge dislocation and the screw dislocation.
No.
Connected group of point defects that forms a line in the lattice structure. These are important later when we learn about cold working, work hardening, something like that. Hi, I'm not Michael Scott. And this isn't Michael Scott. Edge of an extra plane of atoms that exists within the lattice. Sorry, not the lattice. No! Edge dislocation. I didn't understand this picture when he went over it in class. He said it's an edge of an extra plane of atoms that exists in the lattice, but it looks like there's an edge that's missing. I guess this one's extra. Yeah, I guess it all depends on how you look at it. We don't have any calculations during this exam. I didn't have dinner yet. We didn't look at any calculations during this he said that we're not going to do any calculations during this exam, so it's probably going to be real conceptual. Yeah.
I have half a mind to hit you in the head with this pizza box.
Why? Do you think I already ate? Well, I ate some, but I ate things. Do you want gum?
No.
Trident, sweet mint, or meat swint. Meat swint, yes. Where'd it go? I lost the gum. No! Okay, that's fine. Screw dislocation. That's when you got the wibbity wobbities.
Screw dislocation?
No, screw
What's your language?
dislocation. It's a
What's your language? What's your profanity?
It's but
How dare you?
spiral within lattice structure wrapped around an imperfection line like a screw wrapped around its axis. Screw dislocation. Huh? I don't know. Should I have this? I'll just put pictures of this everywhere. Make it small so then you can fit a lot of things on this. It probably won't show up very well in black and white, but If I can't tell what's going on, it's my fault for not studying hard enough.
If I don't get an A, your subscribers are gonna get angry if they don't get A's. You
What?
promised A's.
I promise no A's. No A's are promised. The other thing promised. No, I didn't promise anything. Here, I'll give one Papa John's promo code away right now. This one is for 1 large 1 topping pizza and an 8-inch mega chocolate chip cookie for $15. The promo code is 2 TOPCOOKIE. So it says 2 top cookie. It's a limited time offer. And I'm not sponsored. Interfacial or surface defects. Surface defects, okay. Surface of a crystalline object is an interruption. Grain boundaries are internal surface interruptions, blah, 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 blah. What? Wait, so are grain and grain boundaries surface defects? Let's see. Oh yeah, grain boundaries are an internal surface interruption. Mm-hmm. Each of these chunks is a crystal. And when the crystals grow and smack each other, that's where you get grain boundaries. These are way too big. That's probably fine. Single crystals. Properties vary with the direction. Anisotropic. Should probably be following around with my notes too. Anisotropic. Anisotropic. That means it's not isotropic. Iso is... I don't remember what these mean.
It's hot.
Okay. Oh, water bottle. There's water bottles like everywhere that aren't empty.
Wait, we're ready.
No, I think there's one like over there by the wall. Is that why my sandal is on the other side of the room? You got single versus polycrystal. Wait, no, am I there?
This isn't even open.
What am I doing? Single crystals. Properties vary with direction and isotropic. What properties? What how did I get here? Oh, I'm only on topic 2! Oh, I got 3, 4, 5, 6, 7. I got 4 more topics to do. It's okay, I'm almost done. What does anisotropic mean? Okay, isotropic means grains are randomly oriented. Anisotropic means the properties are properties that vary with direction. So, if grains are randomly oriented, they're isotropic, like these. I'm assuming that these grains are all randomly oriented. What happened?
It ripped off clean.
Oh. Is it because it's Nestle?
Did you just copy me?
No. No. I don't know what you're talking about. No copying happened. What do you mean? Ugh. If grains are textured, they're anisotropic. What?
You heard the man.
The modulus of elasticity in BCC iron. BCC is body-centered cubic. Oh, okay. Okay, that makes sense. Properties that vary with direction are called single crystals are anisotropic if they have properties that vary with direction. Because the modulus of elasticity in BCC iron are different depending on which way you apply the force to on the crystal. Properties may or may not vary with direction. If grains are randomly oriented, it's isotropic. I should probably write that down somewhere. Oh, I can't write there. I'll make a text box or something. Or I just put another picture. I'll figure it out later. Anisotropic. When properties vary with direction, e.g. elasticity. E.g. ergonomics. If grains are textured, you get anisotropic. Yeah, textured grains usually means that there's some sort of crystalline structure because it repeats over relatively long compared to like an atom size. Distance. Electron microscopy. Grain boundaries. What's this? Polymorphism. Two or more distinct structures with the same material. Yeah. That means you get different
I got 95.
on what?
Reflection journal.
Nice. Thanks for warming up the pizza. What'd you do with the olives and mushrooms
What?
that you picked off?
I ate some.
You did?
Yes.
Why?
It was disgusting.
This isn't cold pizza.
It's not cold pizza.
Papa John's. Good cold and hot. Not sponsored.
You don't deserve that pizza. Give it back.
To John? I don't like that anymore. Wait, what? What? Why is there a bite taken out of this slice? Alpha, beta, titanium. Blah, 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 blah. Carbon, you got diamond and graphite. Yeah. The same material can have different crystal structures. Amorphous materials are materials that don't have long-range crystal structures. Long-range order in molecular structure, sorry. An example of this would be glass.
Duh.
That's probably why you can see through it. Because it's not structured, and I think it's...
Clear.
Yes, you can see through glass because it's clear, and it's clear because of the crystal structure. Or lack thereof. And remember, guys, Glass is not a liquid.
Glass is a liquid.
Did I ever tell you about that?
Glass moves
I told you about
very
this.
slow.
Glass is not a liquid.
Glass moves very slow.
Oh my god! Alright. Oh, let's review. Did we learn all this? We went over electronic structure, types of bonding, crystalline structures with types and defects, amorphous materials, lack of order, and differences in melting and solidification. Okay. I don't remember the differences between melting and solidification. Uh-oh.
Glass is a super cool liquid.
Who says that?
Scientific American.
Who says that?
Glass is a amorphous solid.
Mmm!
States somewhere,
Solid!
a state somewhere between those two states of matter.
No!
Yes! That's what amorphous solid means!
Amorphous solid means it's a solid without a distinct crystal order.
It's a liquid. Fly, banana!
Go drink some glass.
You can't drink glass
Why?
because the atoms in the glass move too slow.
So you're saying that you can never drink glass?
Well, if you want to live to be 100 years old, you can probably drink glass.
Okay.
But you gotta start drinking it from when you're 5. Okay. Okay. We're on the same page? Okay.
Blah, 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 book. Blah, blah, blah. I'm a book and I'm boring, said this book.
I'm glass and I'm liquid, said that window.
What?
I'm tired.
Go drink some glass.
I would, but I can't do it because I'm already a quarter way to the 100.
Girl, you ain't 25.
You're right.
You 50.
That's... Stop
What? He's 75? You already 99.
Ah,
Okay. That's not fun for that. With that. Metals have crystalline structures in the solid state almost without exception. Ceramic molecules are characterized by ionic or covalent bonding or both. The metallic atoms release or share blah 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 blah. Ceramics process either crystalline or non-crystalline. Most ceramics have a crystalline structure. Like salt.
I'm changing my name.
To salt. To Michael Scott. Whereas glasses based on silica are amorphous. In certain cases, either structure can exist in the same ceramic material. When this mineral is melted and then cooled, it solidifies to form fused silica, which has a non-crystalline structure. Polymers have many consist of many repeating mers. How many mers you got? Cause I got a lot of mers. Cause I'm a polymer.
Just living on the floor.
Huh?
And I'm calling the police. And I'm recording your channel.
We're pretty much just don't for what? For what?
Copyright.
Subscribe to PewDiePie. Mechanical properties of a material determines behavior. Oh wait, yeah. Let's figure out what chapter 3 is all about. Boop. Topic 3. Physical properties of materials. Mechanical properties. Similar enough. Got volumetric and melting properties. You got thermal properties. Got mass properties. Mass diffusion, sorry, and electrical properties. You ever not feel like studying? So then you just don't? And then you get to the exam, and then you find a question, and then you're like, I would have known the answer to this question if I studied.
Are you making fun of me?
Happens to me every exam. No. Huh?
I'm gonna shop.
Shop? What?
Shop.
Shop? For what?
Eyelashes.
Shop for eyelashes?
They do eyelashes.
Real ones? Do they make real false eyelashes? Where do they get the hair from?
Should I get? That's a good question, Jay.
Hmm?
Where did they get the nails from? Can you give me a number?
28.
Okay, I'll spend only $28.
Oh, jeez, Kristen. I gave you 28 cents. Density, thermal expansion, melting point, atomic vibrations due to heating, thermal expansion. What do we need to know about this section? Density, thermal expansion, melting, and diffusion. It's like nothing.
A humidifier?
In general. Right? In general, the density decreases with increasing temperature, right? In general. Now there's one thing that's very common that breaks this rule, breaks this generalness. Do you know what it is?
Glass.
Water.
I was close.
You know.
Because water is a liquid.
No!
Glass is also a liquid.
No! God, please, no!
Michael?
No! No! Water, the density decreases when you freeze it. How did you get the exact spot? Volume per unit weight increases with increasing temperature. Yep, you get that. And temperature. Oh, maybe I should probably look at this. Ooh, look at that. This is the tale. Probably can't sing that. No singing. Captain Jack Sparrow, pirates so brave, the seven seas. Ba, 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 da, 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 da. I wonder if I can do this. Do that with everything. Okay. Everything will be square. Everything will be square. You are square. Yes. So top. Tip top shape. Ah! Move! Move! No! How can I have Microsoft Word on my resume if I can't get it to move? Oh, there we go. And then open the door, pull out a chair. You can tell me how your day was, but I don't really care.
Do you want an apron?
Do I want a what?
Apron?
Apron? Not really.
A lot of this stuff is $2 and it's very dangerous, Piggy.
Stop it. Thermal expansion in manufacturing. You can use it for a shrink fit. That's when you get something cold and then you put it back into something, and then when it gets warmer, it fits. Thermal expansion can be a problem. Welding, blah, 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 blah. Melting of pure metals. Heat of fusion. I know what that is. Melting of metal alloys. Wait, what? TM is the melting temperature. Melting of alloys. Alloys don't have a single melting point. Oh, this is where we talked about phase diagrams and stuff. These are pretty important. Maybe I can look at this.
It's $16.
You know what else is $16?
The bag that I want is $16.
160 chicken nuggets from Burger King.
You know that because you've done that before.
No, I've only done 100.
No.
I've only done nuggets in the 100.
How come you didn't upload the nugget challenge then?
I didn't do the nugget challenge. It wasn't the nugget challenge. You guys want to see a nugget challenge from this channel? Alright. Post in the comments how many nuggets you want to see me eat in the nugget challenge. Nuggets or we riot. Hey, where'd the text go? What? Is it hiding? Oh, it's right there. Oh, this is a travesty. Alright, this is so I remember these words. I guess I can't remember them if I can't see them. Why do you like this? Go like this, and go like this, and go over here or something. Bring the front, go over here.
There's only one crayon left.
Ah. I guess I'll just remember what that is. Looks like we're going no text. So I want to insert a text box. How to insert a text box. Like this. Go here and click text box. You want a simple text box because whatever. Anisotropic. When shape. When Move the. There we go. Save this as. Where's the. It's gonna be. It's gonna be. On this PC.
Oh, that's a lot. Hey, I have these.
Would you look at that? In non-crystalline materials, glasses, a gradual transition from solid to liquid state occurs. Huh.
I'm not I wasn't listening. Say it again.
I don't have time. I'm running out of time.
Ah, okay, big news.
All right. In half an hour, I will reveal the next Papa John's promo code. I wonder if it's or if it's location specific. Wouldn't that suck? Ah, yes. Fun fact. The linear coefficient of thermal expansion is a material property, right? And based on the three broad categories of materials that we have: metals, ceramics, and polymers. Polymers would expand the most. Second would be metals, expanding the second most. And ceramics would expand the least. We can think about it, come to this conclusion ourselves through thinking about the way that they bond. The tight ionic bonds require a lot of energy to break. So they probably don't really expand that much before they just shatter.
I'm overwhelmed.
Hmm?
I'm overwhelmed.
By what?
The amount of things I could buy. It's all random.
How many days has it been?
It's been over. It just started getting to it.
It's been like a week. Alright. I don't know what sintering is, and I lost my notebook. I found my notebook. Still don't know what sintering is. Melting, heat or fusion, melting of non-crystalline materials. After they hit the melting point, there's like an elbow. Thermal properties, blah 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 blah, diffusion. You know, I think I'll be okay for this exam.
That's what I said.
I wake up and go to class in the morning every Monday, Wednesday, and Friday, and I pay attention. He told us to read the book, but I never read the book. Maybe I'm not okay for this exam. Diffusion is mass transport by atomic motion. Motion in the ocean of electrons, the sea of electrons. Metals. Metals diffuse within the sea of electrons. We are interested in the solid state. Solid state, solid, snake. Self-diffusion in an elemental solid. Atoms also migrate. Because they do. That atom over there, sometimes it just travels across the room. Probably not that much. Unless you have a really small atomic size room. Interdiffusion. Even within an alloy, even within solids, atoms diffuse.
You know what I'm gonna do?
Diffuse. Hey, I was gonna do that at you, but you would have been mad and kept on shopping for like 2 hours. Holy moly! I can figure this out. Magnitude of diffusion coefficient is indicative of the rate at which atoms diffuse. Okay. Sure. What? Diffusion increases with an increasing diffusion or increasing temperature. Sure. Dope the silicon to make it semiconduct. Oh yeah, that uses diffusion. Electrical properties. Electrical engineering materials exhibit a great variation in their capability to conduct electricity. Like copper conducts electricity really well, while wood doesn't. Dimensioning surfaces and the whoa. Did I miss a day? Nah, electrical properties, blah blah blah. Metals are best conductors because metallic bonding. Ceramics and polymers are probably poor conductors, and many materials are used in blah 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 blah. Alright. I found it. I found it. I have found the gum. The Trident Minty Sweet Twist. Artificially flavored. Ah!
Of all the angles you could have thrown it at.
No one saw that. No one saw that. This is a no camera stream.
Oh my god. Aw. That was funny.
Alright. Did we get density? Yes, we know what density is. Thermal expansion. Yes, we know what thermal expansion is. Melting. Yes, we know what melting is. Diffusion. Yes, we know what diffusion is. Cool. Let's go to topic number 3.
Why did you take from the bottom?
What?
Are you okay?
Do you get trident a lot?
Really?
What do you mean, why did I take from the bottom?
Why did you take from the bottom?
That's the bottom? I opened it like this, and I was holding this. So I took this. What? That's the outside, right?
Your pillow's bad for my hair.
You're bad for my pillow's hair.
It pulls my hair out.
Why does it pull your hair out?
I don't know.
What's wrong? Let me put a plastic bag on it.
A plastic bag won't work.
Would work? You actually want that?
No.
Because you roll around, it'll be... I'll be like, what's that? Wrestle. Alright. Electrical properties. No, we're not doing that. We're looking at dimensions and surfaces. Okay, this is going to be pretty short. We got surface texture, 4 features, and surface integrity. Let's look at what the...
This gum looks nothing like that. It's like chalk.
What? Chew it!
Why?
You're just sucking on the gum.
No, I'm not. I'm licking it.
Just stop licking the gum. I'm gonna be okay. This is the wrong topic. What? Oh,
Distracting you?
you are not distracting me.
Are you sure?
My stream is distracting me. I'm gonna be like taking the exam, and then I'm gonna be like, I'm gonna want to be talking out loud during the entire exam, and that's a big no-no. I'm gonna be like, oh, surface texture. I remember 4 feature. And it'll be like, shh. And I'll be like, you, give me your exam. And I'll rip it in front of the whole class. And I'll be like, oh man, come on, professor. Dimensions, surfaces, and their measurement. Let's see. We're going to learn about the definition and types of tolerances. We're going to learn the types of surfaces, and we're going to learn 4 elements of surface texture. We're also going to learn about surface integrity. All right. Dimensions. That's the dimension. Tolerances. That's how much we allow them to allow a material to be manufactured differently from the nominal dimension. So if I tell you to make a steel rod that's 1 foot long, I have to tell you how close to 1 foot it has to be. It could be plus or minus an inch.
1 foot.
Huh?
Why can't it just be 1 foot?
It's really expensive to make exactly 1 foot, to make something exactly 1 foot.
That's stupid.
What?
Why?
What?
Why?
What do you mean why?
Why?
The precision is expensive. Precision takes money, it takes time, it takes expertise.
If they're good at their job, then it wouldn't take much.
First of all, you have to find out how, you have to find a way to measure that it's exactly 1 foot.
A measuring tape, duh. A ruler.
A ruler can only go so fine.
1 foot.
If it's 1 foot and you want to get it exactly, you have to like shave it and stuff with a planer. Takes time.
Excuse me.
Sit down. No, you may not use the bathroom. I'm kidding.
Hey.
Hmm?
Never
What? Alright, we know what dimensions and tolerances are. ANSI 14.5M 1982.
Glass is liquid.
Glass is not liquid.
Glass liquid. And water's not wet. Whatever.
Well, what does wet mean?
Wet is water.
What?
Mhm. And the Earth's flat.
Yes, we all know the Earth is flat. Measurement. Measurement systems. Yeah, we know about this. Accuracy and precision. Yeah, we know about accuracy and precision. Surfaces. Haha. This is when it starts getting interesting. Nominal surface is the designer's intended surface. So if I write on the the engineering drawing that this surface needs to be shiny, that's the nominal surface.
That's the extra surface.
Oh, it's not. That's when you draw edges that are lines. Actual surfaces are determined by the manufacturing processes used to make them. For example, sand casting. When you use sand in sand casting, do you know what sand casting is? You get a thing, right? The thing in the shape that you want to make. You put it in some sand. And you put it another block of sand on top of it. Press it up together. Take it apart. Take the thing out. Then you got a sand mold, right? Then you put it together. You pour the metal in. Then you open it and you get a part, right? But because we use sand casting, that determines the surface of the mold, or the cast, sorry. It'll be all bumpy and stuff because sand is bumpy. Coolio. Now, why surfaces are important? Because you want it to be pretty, safety, friction, wear. Sometimes it can impact mechanical and physical properties. Part assembly and electrical contacts. Sure, cool, nice. Surface technology concerned with dividing blah 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 blah. Metallic part surface. What? Where's my water bottle? I'm dying over here. Blah 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 blah. But what are the 4 features? Aha! 4 features! Roughness! That's when you get small, finely spaced deviations from the nominal surface. They gotta be small, and they gotta be finely spaced. Then you get waviness. Deviation, but with larger spacing. You can see this, like, it's like the difference between, scratches. Kristen? Like scratches, or big, like using a comb and making big raking things. Like sandpaper and brushed aluminum, I guess. Lay is the brushed aluminum. What the heck is waviness? Roughness is superimposed on waviness. Oh, waviness is just bigger roughness? Oh, sure, whatever. Remember that. In order to remember this, I will not write it down on my cheat sheet. Is that a good idea? Krister. Co-host. No! Yeah, fine, sure, I'll write that down. Yeah, we'll just call this brushed aluminum. I got really quiet because I was chewing a pizza. Speaking about pizza, the giveaway code is gonna come out in 10 minutes! I wonder if I need this. Probably not, but let's find out. I mean, let's not find out. I'll have this anyway. Don't do that. Whoa there. Hello? Why you gotta... I'm running out of space! Behind text. That's okay. Alright, we got the 4. Nope, we're on the 4th one. Let's look at this. Flaws. Yes, flaws. You got cracks, scratches. What are inclusions? These also affect surface integrity. Alright, now that we know that they also affect surface integrity, let's bump down this. Ah, I spelled it wrong. Alright, what else is on this list? Surface integrity, nice. Just for fun, we will do roughness is quantitative, finish is qualitative. Got equations for roughness, probably don't need that. Holy moly, if we need this, I would be out of luck. It's an integral. Fancy schmancy. Surface roughness specification. Oh, maybe I need this. Oh, no. Why? No! Let me click on nothing! Why do you do this to me? Hopefully I can read that come exam time. Coolio. Alright, let's put in what surface integrity? Surface. It's the study and control of the subsurface layer and the changes in it that occur during processing, which may influence the performance of the finished part or product. Mechanical, thermal, chemical, electrical. Stress in the subsurface layer, mechanical. Cracks in microscopic, macroscopic. Mechanical, metallurgical changes, thermal, corrosion, chemical, changes in conductivity, electrical. Okay, cool. Surface texture, geometry of the surface, surface integrity, deals with material immediately beneath. Measures of roughness, stylus equipment, nanoscale roughness. Results, evaluation of surface integrity. So you get the roughness, layer orientation, visual inspection of cracks, hardness testing, microstructural investigation, residual stress analysis. Oh, chapter 6 is going to be a dozy. Chapter 6 was so big. Then metal casting. Man, there is a lot left. Not even halfway done. Well, I guess it's only been an hour and a half of studying and basically me talking the whole time. Let's reload this and good. Stream is healthy. Stream options, enable DVR. Is this education? Yeah, it's education. Three minutes. We get the Papa John's. Surface integrity is, what is it? There's a nice, I guess I'll just copy this. Changes to the subsurface. Uh-oh. That resulted from the processes that created it. Don't make fun of my typing. Probably bold this so I can see it. What else? What else? What else? Visual inspection, tolerances. Machines generally accurate. Sandcasting, inaccurate. Gotta have big tolerances. Some processes are inherently capable of producing better surfaces than others. Honing, lapping, polishing, super finishing. Cool. Done with topic 4. On to number 4, topic 5, metals. Melting casting. Ah, jeez. And, where's 6? Where's chapter 6? Then part 2? Yes, part 2. Part 2, part 2! Metals. Shoot. These are the long ones. No! My brain's tired! Okay. Enough of that. In this topic, we want to get the definition of metals. We want to be able to get the types of alloys. We want to be able to read phase diagrams. We have to learn how to identify the number of phases, the composition of each phase, and the relative amount of each phase. Then we gotta be able to identify phase transformations. We got the different kinds of phase transformations. Oops. We gotta look at iron and carbon alloys. I don't need all these. I think I know what a point defect is. Maybe I need this though. I'll need this later. Might need this. Might need this. Might need this. This can just be there. Open a bunch of space up here. Okay. Okay, iron and carbon alloys. Cool. Let's open up the PowerPoint that our professor gracefully provided us with. Classification of metals and metal phase transformations. Fun. Very fun. Got the criteria for solid solution. We got the interpretation of phase diagrams. We also have the 3 primary metal phase transformations. And last, but of course not least in any sense, is it the types of metal alloys. Okay, cool. Melting of metal alloys. Here you have a phase diagram for nickel and copper alloy system. As you can see, nickel and copper are completely soluble. Can you hear my watch? Anyway, state of equilibrium. Never completely achieved. Small changes may occur, may persist indefinitely. Okay, cool. Solid solutions. Hey, that's one of the things we need to know, right? Definition. Oh, oops. Definition of a metal. Oh, I know the definition of metal. That's a metal. Also, metal and metal. Crystal structures maintain impurity atoms are randomly distributed distributed throughout the host. For interstitial solid solutions, impurity atoms fill the empty spaces or interstices between host atoms. Interstitial solid solutions what? That's when you get the molecules that are big. I mean, the atoms that are big mixed with the atoms that are small, and the small ones are between the big ones. Like carbon steels, carbon iron. There might be a picture of it somewhere. Might want to. No, it doesn't look like there's any pictures of that anywhere here. Oh, jeez, my brain's so tired. Oh no. Sorry about that late promo code. Here's a lunch special. One small, one topping pizza and a 20-ounce drink. $7.99. Online promo code TAYLORLUNCH. That is Taylor Lunch. 10 a.m. to 4 p.m. daily. Limited time offer. Oh, they also have a carryout special. $6 for a medium one topping pizza. Promo code carryout6. Hot oven. Wait, hot from our oven to your car. Papa John's. Better ingredients, better pizza. I am not sponsored or supported by Papa John's in any way, shape, or form. Except I bought a pizza from them yesterday, and I'm eating leftover pizza. Alright, solid solutions. Atomic diameter of interstitial atom has to be a lot smaller than the host atom. Not favored for dense structures. Generally, max allowable concentration of interstitial impurities is less than 10%. Cool. Let's see what my notes have to say about that. Fundamental concepts, components, systems, solubility limit, phase, equilibrium, metastable. Isomorphs are any percent of either for all concentrations. They are mutually soluble. Oh, that's from the phase diagram of copper and nickel. Solute is the thing that's being dissolved, and the solvent is the thing dissolving the solute. I'm a solute. Salt is the solute. Water is the universal solvent. Nice. Nice. Solid solutions. Crystal structure is maintained. Impurities are randomly distributed. Interstitial atoms. Oh, yeah. Impurities in metals. Substitution. Null. Substitutional solid solution. What? Oh, yeah, okay. So nickel and the nickel copper alloy is a substitutional solid solution. In order to have a substitutional solid solution, you need the difference in atomic radii to be less than 15%. They have to be pretty close to each other in the periodic table. They also need to have the same crystal structure for when they're pure metals. It's like they both have to be BCC or both have to be FCC. They both have to be member FDIC and all that jazz. HCP, is that one? Hexagonally centered, hexagonal close pack, yeah. Valency, all else being equal, a metal will have a greater tendency to dissolve a metal of higher valency than one of lower valency. Now, let's figure out what valency means, because I forgot what valency means. Want to know how to do that? You go here and you Google valency. That's not how you do it. Valency. Another term for valence. The combining power of an element, especially measured by the number of hydrogen atoms it can displace or combine with. Carbon always has a valence of 4. Okay. So, basically, valency is the amount of things it can accept. The metal have a greater tendency to dissolve a matter of higher valency. So, If a metal has higher valency, it'll probably be dissolved by one of lower valency. That means the metal of higher valency is the solute, while the one of lower valency is the solvent. The lower valency metal, that would be like, I don't know, sodium, where it only needs one. Okay. So to make a substitutional solid solution, you have to have close atomic radii, you have to have proximity in periodic table, you have to have the same crystal structure, and you also have the valency. That is probably important to note. I'm gonna make a. I'm gonna continue this. I'm gonna make a new text box just for that. Just for that. Jolly good. Tea and crumpets. Do you know the code for make delta? Delta code. No! Alt 235. No, I want capital delta. Oh, they don't have one. Oh, I'll just copy it from here. Lol. Delta R. Oh no. Why are you Arial? Be Calibri body 9. Calibri 9. There we go. Delta R. 2. Proximity in table. Electronegativity. And 3. Tin crystal structure. And pure metal. And 4. Valency. Cool. Cool. Nice. Oh, there we go. Nickel and copper. They got the same FCC crystal structure. The electronegativities are pretty close. And the radii are even closer. That means they are totally soluble in one another for all proportions. Okay, phase diagrams. This is where things get hot and heavy. Literally, look at that. Temperatures upwards of 100 degrees Celsius. That's boiling. That's pretty hot, but it's not as hot as this. Temperature is at 1,600 degrees Celsius. That's super hot. Don't touch that. You will burn your hand. Get like 3rd-degree burns and stuff.
Don't let me sleep.
Don't let you sleep? I already did. You slept for like half an hour or something. Yeah, but you could do it today, and then you would have less that you have to do tomorrow.
I deserve the world right now.
Huh? You what?
Deserve the world.
You deserve the world right now? I don't know what that means. Well, I'm going to be taking a quick studying break. And, what should I do during this study break? Okay, figuring something to do during my study break is too hard, so I'll just keep on studying. Phase diagrams. Solubility limit, liquid solution, liquid and solid. What's that? Oh, that's just a line. Okay. What is the solubility limit for sugar in water at 20 degrees Celsius? Okay, so you go to the water at 20 degrees Celsius, then you go until you hit the line of solubility limit, and then you go straight down, and then you'll get the percentage, weight percent sugar. You get 65 weight percent sugar. Solubility limit at blah 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 blah. So that's more sugar than it is water. Cool. Components and phases. The elements or compounds which are present in the alloy. Ergo. What is e.g.? Aluminum and copper. Phases. The physically and chemically distinct material regions that form. Like alpha and beta. Alpha is the darker phase. Beta is the lighter phase. This is the aluminum. This is an aluminum, a picture of an aluminum copper alloy. So you go over here and you look at this and you're like, hey, altering the temperature can change the number of phases. And altering the concentration can also change the number of phases. Over here, you have one phase present. It's just liquid. Then over here, you have the liquid and the solid sugar phases present. Okay, over here, it's like you got liquid and you also got the floating sugar because it's not dissolving. That means this is a phase and this is another phase. It's kind of different from phases and how you would think about them. Over here, you got a liquid phase, you got a solid phase, and you got an in-between phase. This is liquid plus alpha. Alpha is solid solution. So there's 3 different phase fields. 1 phase field, 2 phase field, 3 phase field. There you go. To figure this out, you gotta go here, and you gotta go down, and you gotta go here, and you gotta go down, and then something in the middle, or I don't remember. Oh, that's how much liquid there is. That's how much alpha there is. Okay, this system's binary. It's also isomorphous because it has complete solubility of one component. Isomorphous. Okay, how do you determine the phases present? How do you know this is 35 weight percent nickel? Oh, at this point it's Ln. Liquid plus alpha. Haha, the tie line. Bless you, thank you. Alright, tie lines are very important. You use them to figure out stuff. So, I think the question is rule 2. Wait, what's rule 1? If we know the temperature and the concentration, then we know which phases are present at that point. Yes. Simple. That's just how you read a graph. You match up, you find the temperature, and you go this way until you find the percentage that they give you, and then you just read what's over there. Okay, rule 2. If we know the temperature and concentration, then we can determine the composition of each phase. That means how much of each phase is in the thing. So at this temperature with this concentration, we'll have this much percentage liquid mixed with this much percent solid, alpha solid. So consider 35. Okay, we draw this and we go to the left and to the right. That's how you make a tie line. TB, that means the CL and the CA. What does that mean? What? Alright, let's learn what liquidus and solidus mean. Now we're not just talking about snake. Alright, so, oh, this is just going off of this. At temperature A, yeah, A, only the liquid is present. Yes, yes, yes. At temperature D, only the solid is present. Yes, 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 yes. But at temperature B, both are present. You have 32, that adds up to 75. What does that mean? Oh, sorry, that's what it means. So it's made up of, well, we can also determine how much of each phase. The weight fraction of each phase. Okay, so that makes sense. So when you're here at the tile line, that means that the liquid that you have is composed of 32 weight percent nickel, and the solid that you have, the alpha solid, is composed of 43% weight, 43 weight percent nickel. Okay, so that tells you the composition of the phases present. The composition of the phases present. Now, to do this, you can do the measuring thing and get that. Or, there's another way to do this, right? S over R plus S. Or, it's, what? (43 minus 35 over 43 minus 32? What is that? What's 35? (43 minus, oh, okay, 43 minus 35 over 43 minus 32. 43 minus 32 is the entire zone. And you get the weight fraction, and that's how you do it. Okay, cool. I think I can figure out how to do this. I can remember this. I can totally remember this. I'll take a break at 10. 10. Should I turn on some music? Is that what people want? Is that what the people want? There's my water bottle. Vata! You guys hear that? Pretty crazy, huh? Pretty crazy, huh? Haha. Okay, no, I'll turn that down. Sorry. Should I put more gain on this? No, it's fine. Ah! 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 It's peaking too much. Too much peaking for my liking. Oh, whoa. What happened there? Cooling. Consider microstructural changes that accompany the cooling of a C0. That when you cool it, okay, I'm considering the cooling. Oh, this is what the cooling looks like. Got this, all liquid, and then it grows these crystals at B. 35. You can figure out what this is because you draw the tie line to over here. And as the tie line shifts from this side being green to going over here, you get more and more growing solids, alpha solids. So then in the end, you're left with totally alpha. Now this is just with the thing of the copper nickel system. Solid solution strengthening. Oh, at 60% you get the highest tensile strength and the lowest ductility. Interesting, interesting. Copper is really good at being ductile. So copper is more ductile than nickel, but when you combine them over here, they get really not very, they get really non-ductile. Copper has low tensile strength, lower than nickel. But when you combine them, they get bigger tensile strength. Look at that. Alright, binary eutectic. Eutectic is an important word. We need to know this. Eutectic. That is when a liquid goes to a solid and solid. Paratectic. Ah, that's kind of like me. Goes lamellar. Oh, nope. Let's go to eutectoid, I guess. Eutectoid is where it goes solid. Oops, sorry. Solid into solid plus solid. It's like eutectic, except with solid. And paratectic, that's the one that's kind of like me. So solid plus liquid gets to be a solid. And that doesn't fit in one line. So it is a travesty. How do I fix this? I have no idea. Alright, fine, I'll do it. No. S1 plus S2. Build this. Build this. You got S1 into S2. Shoot, really. S2 plus S3. Paratectic, you get the S1 plus L1. I guess it's just plus L. No, don't do that. And you get S3. No, 2, sorry. And these arrows are two directional. Oh! Does this work? Can you do this? Oops. Maybe if I start off with I guess I'll just keep it like that, huh? I don't need no fancy arrows. I understand what this means. This is left L to R is heating. Sorry, what? Oops. Left to right is cooling. Whew. That would have been bad if I had that on the exam. I'd be like, nothing makes sense. Alright, the way you find things out is the same. Except over here, you get a liquid and then it melts into two different things, regions. This is an easy tie line. Over here, you can probably find out. If it's over here, you can find out that this is a mixture between liquid and alpha. Over here is liquid and beta. Over here is the beta and alpha region. Cool. Lamellar. Okay, so that is this part. Okay, ID phase transformation. Okay, I can do that. Yay! Wait, did I get the types of alloys? What are the types of alloys? Oh, what are the types of alloys? I don't know. Classification metal alloys. Ferrous and non-ferrous. Is that what it is? Man, I wish I had the quizzes back. I'm a noble metal. I'm expensive. Oi! 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 Where's the... fundamentals of casting. I'll get casting later. Metal casting processes. I already have a sheet on that. I can probably figure it out. Haha. It is 10:04. The time is 10:04. Ah! Something fell. It was small. Uh-oh. That's not right. Okay, that's confusing. Hmm. Okay. Types of alloys. Ferrous, non-ferrous. Ferrous, Beeler. Oh, is this the type of alloys? Hmm. Let's see if I want to picture this. Yeah, I'm kind of running out of space, but... Oh no, don't go there. Cool, now I can make it go anywhere I want. Ferrous alloys. Ferrous alloys. Contain ferrium or something. I don't know. It's iron. It's like Latin or something. Oops. High density, relatively high density, and what's that sound? Ah! Am I being haunted? Hello? Where am I being haunted from? What in the world? You guys can't hear it. Oh, I just sound like a crazy person. Low electrical conductivity. Generally poor corrosion resistance. Oh yes, my professor told us a story about his metal stairs and how they got blasted and the sand got in and then it got all rusty. Okay, steels are less than 1.48% carbon. Cast irons being 3 to 4.5% carbon. See, the tensile strength and hardness goes up as you increase the amount of carbon inside it. Tensile strength and hardness as a function of carbon content in plain carbon steel. Cool. Whatever. Low alloy. Increasing strength, cost, and decreasing ductility. Is cast iron expensive then? What the heck is steel? Oh. Okay. High carbon steel. Low alloy, high alloy. I'll just include this just in case. Just in case. You can be behind the lines. No, you can be in front. Go in front. Alright, do I know what cast iron is yet? Kind of. I should probably be able to read the thing. What is it? Okay. Time to look at my notes. Solid solution, eutectoid, paratectic, whatever. Oh, that's the beginning of this month. That's like 3 weeks ago. The first one means, being a 1 means plain carbon steel. And the last 2 give carbon concentration. Okay. Like this. This is a plain carbon. That means it's 1. This is an alloy carbon, which means it's a 4. Plain, alloy, plain, alloy. Cool. This is just stainless steel. It's different. General properties. 200 megapascals. Yeah, let's just say that. And a tensile strength of 80,000 pounds per inch. What's that? What is that? What is steel? Is steel just ferrous carbon iron? Yeah, steel is just carbon iron. Classification of metal alloys? Aha! Cast irons. Cast iron. Low melting point. Of course. Not too sure what to do about this. I don't know. I'll tell this one can be behind this, but this one, the fill needs to be invisible. How do I do that? Let's see. Go on review. It's in design. Then draw. Then insert. Format shape. Aha, fill. No fill. There we go. Line. No line. Okay, cool. Okay, let's write gray iron, flaky, graphite, for vibration damping, ductile iron. What? I guess I'm just copying this though. Go away. Ductile iron has Mg or Ce or crankshafts, gears, and car parts. graphite iron is 1 weight percent. Silicon with perlite and cementite. Very hard and brittle. Cast machine used in rollers. Malleable iron. Using doubly strong and ductile. Gears, pipe fittings, valve putts. Alright, let's bolt some stuff. Gray iron, ductile iron, white iron, malleable iron, cast iron, and steel. Compacted graphite iron. What the heck? Compacted graphite iron. Diesel engine blocks. Resistant to thermal shock. No! I'll spell it with a K. That's fine. That doesn't have to be a word. Stable relationships between phases and alloy have to be equilibrium phase diagrams, binary diagrams, given composition at specific temperature, phase is present. Their composition's relative amounts may be determined within two phase regions, tie lines, and lever rule. What is the lever rule? No idea. Eutectic, know what that is. I wrote what that is. Eutectoid, wrote what that is. Paratectic, wrote what that is. FE3 phase diagram is one of the most important systems. Several FEC alloys result. Additional alloying elements after. To form pure metals, the metal product is often reduced from ores found in nature. Yes, of course. Generally, alloying of metals is done to enhance the properties. The metal of choice will depend on the capability to tailor its properties for the desired application. Cool. Well, I'm going to take a bathroom break. How do I do this? I will add in text. Call it bathroom. It will say bathroom. It will be in autumn font. The color will be, oh, that's fine. That's an okay color. The color will be some type of cyan. Okay. Where is it? What the heck is it? No! Oh wait, no. Did I already put it in? You. Get bigger. if I can make this look better. No? Oh, the size is really small. Oh, that's really big. Okay. How about size is 500? It's a pretty good size. Cool. Well, I'm back from the bathroom, and I don't know what this is. I guess I'll just remove this. Okay. Running out of space. How am I gonna have all the molding stuff? Alright, let's look at some fundamentals of metal casting, I guess. Stages of metal casting and development of microstructure during solidification. Anything that I don't understand? Melt the metal, pour it in the mold, let it freeze. Capability and advantage of casting. What's in that shape? Big parts and small parts. Foundries where you make the casting. Mold, open molds, okay. Do I need that? Do I need that? Do you know this? Open versus closed? Yeah, I know that. Permanent versus expanded? Yeah, I know that. 3 stages? Yeah, I know that. Various metal casting techniques? Yeah, I know those. Casting defects? Yay! Might need to review that. Product design considerations? I don't know. How about I add this picture over here? Just for safety. Put that over here. No, move. Dang it. In front of text, whatever. Actually, I don't know why I need this part. Whatever. Spendable mold, permanent mold, advantages, disadvantages, part shapes and permanent mold. Limited, need an open mold. More economic and high production operations. Memorize this. Nah. Cope and drag. Prying line, wall cavity. Use of a core, gating system. That's the downscrew and pouring cup. Riser. Has to freeze after the main casting. Just remember that. So then you can keep filling it up as it fills the thing. Heating the metal. Heat it up. Pour it in. Memorize this again. Uh, huh. Cooling curve. I'm gonna have to draw this. Pouring temperature right here. Liquid cooling, cools, and then freezing begins. It stays at this temperature for a long time. And then, once it's done freezing, it'll keep going down. Solidification of pyramidals. Due to chilling action of mold wall, thick skin dissolves for interface immediately after pouring. Skin thickness increases for a shell. Rate of freezing depends on the heat transfer of the mold as well as the properties of the metal, of course. And it gets this kind of grain. Remember that? Dots on the outside, lines to the inside, perpendicular from the wall. Look at that. They match up on the graph. Isn't that cool? Slow rate of cooling, okay. First alpha to solidify. 46 weight percent nickel. Why would that be? Oh, there we go. Then 43, then 36. Interesting. It's Voronof's rule. Gross. I had to do this for the project. I probably know how to do that. Shrinkage happens. You told us to memorize it. Oh, I didn't memorize it. Thin section. Cool. I probably will be okay on all that stuff because it's pretty fresh in my mind. Alright, casting processes. Expendable mold, permanent mold, sure. That's sand casting. Steps in sand casting, making the sand mold. Oh, core. That's the core. Chaplets. Interesting. Strength, permeability, thermal stability, collapsibility, reusability. Cool. Foundry sand. Foundry sand. Oh, I might need this. Alright. Time to get typing in what looks like to be the last text box. You got strength. You got permeability. You got what really? You got thermal stability. You got collapsibility and reusability. Interlocking. Irregular grain shapes. String. That's silica. That's SiO2. Body clay, huh? %90 sand, 3% water, 7% clay. Okay, green sand. Sand, clay, water. Green means has moisture when pouring. At pouring. Dry sand. Organic binders. Other than clay for dimension control. Oh jeez. Baked. So what? Nope, not hard. Skin. Oops, sink. Trying. Alright, so I got, let's see, shell, vacuum, expanded polystyrene, investment, plaster, or ceramics. Any list of defects and okay. Maybe I need to kill that. Yeah, don't grab it. No! And there we go. Over here, make this longer. Plaster, ceramic. Got it. Oh, the vacuum molding is. Let's see. Unbonded sand is held in the flask with a vacuum. Sure. Permanent is basic dye centrifugal. Open. Defects. Defects. Cool. And maybe we'll fix some of the defects. Misrun. It's cold shut. Oh no! That's unfortunate. I put my notebook on top of the food thing. So now it's all gross. Ew, yucky. Remember that, kids. Always look before you put your notebook on top of stuff. Words to live by, I guess, kind of. Oh, I guess I'm uh-oh. Put that over here then. Quickly come out. I don't know what to do with these order forms. Caused by a too low pouring temperature. Reorient the mold cavity, add risers. Reduce distance between source of material and the cavity. Increase the pouring speed. Also, yeah, that's it. Also increase the pressure between the two halves. Cold shots faced with the same stuff. I'm probably think those up. Cold shot is bubble cavities. Probably fix that with gating design, sprue design, runner design, riser design. The design of it. I could reduce the pouring speed, redesign the mold, redesign the sprue. Decrease the pouring temperature as well. Stop it! Shrinkage cavity. Depression in surface or internal void caused by solidification. Shrinkage. That restricts amount of molten metal available in last region to freeze. Use cold things. What are they called? Colders. Risers? Ah, geez. They're in the other one. Ah, external chills. Ah, it was last week. Alright, shrinkage cavity. What the heck is that? Oh, I just wrote about that. What? Oh. Sand blow. Sand blow. Gas caused by gas bubble from mold. Pinholes. Gas cavities. Ah, come on. Penetration. So no mold. That looks scary. Mold shift. Cool. Cool. Foundry inspection methods. Can detect obvious stuff, dimensional measurement, ensure tolerance is met, the metallurgy, chemical, and other tests are concerned quality. Ferrous casting. I wonder if I need to know these. Got defects, got metal techniques, got 3 stages, heating, pouring, and solidification. Product design considerations. Simple geometries, corners. Okay, I got this. Simple geometries, corners. Fillets. Tolerances and finish. Like machining allowances. Almost all sanding will be machined to achieve the required dimensions of the future. Additional material called the machining allowance is left in the casting in those surfaces where machining is necessary. Typical machining allowances for sand casting around. Oh, I didn't do that. In the design. Oops. Cool. And that is the end of studying. Ah, we did it. We made it 3 hours straight of studying. Oh, I'm so proud of myself. Oh, I learned so much. I'm gonna do so well on this exam. All right. Next time you see me, I will have updates on how I do in this exam. I know that I'm going to perform. Fine, I'll be fine. Alright, let's do something fun. No, I mean, when you're done studying, you should really review the main points of everything. Fine, okay, I'll do that. Alright, can I go through this in a minute? Okay. Nature of materials. Okay, electronic structure, that's the electrons, types of bonding. We got 3 types of bonding that we're going to look at. We're going to look at covalent, we're going to look at ionic, we're going to look at metallic. Covalent is fine. Metallic is sea of electrons. Ionic is really strong. Crystalline structures. There's a bunch of types of stuff. There's defects, point defects, and so and so. Amorphous materials lack order. Melting and solidification, the processes are different. There you can draw it, whatever. Physical properties, density, and you know what that is. Thermal expansion, you know that gets bigger when hot is less dense, so bigger. Melt, yes. Diffusion is the movement and stuff. Dimension and tolerances, there's 4 features. It's written down. There's roughness, other roughness. There's lay, and there's cracks and stuff. Surface integrity, that's below everything. We got things. You got metals. You got phase diagram, you got a tie line, the iron and carbon, and the molds. There's open and closed mold. You pour it in, and cool. That's 3 hours. Nice. Good review. All right. I'll catch you guys on the flip side. Thanks for tuning in. I hope you learned something. I learned nothing because this was all a review. I did the learning beforehand. And take everything I say with a grain of salt because I usually don't know what I'm talking about. I will see you next time. It's been great. It's been fun. Thanks for watching. My name is Perry. And goodbye. Don't forget to follow me on Twitter for fun. I'll be at Picky Perry. That's PIKIPERRY at PIKIPERRY on Twitter. I actually don't post anything on Twitter, so maybe that's not even. I might start posting stuff. Depends on how this channel goes. You can also find me on Twitch, but I'm gonna be on YouTube doing stuff on YouTube, so I don't know why you want to see me on Twitch. Bye, guys. Have a good night.